In this module, we will extend our understanding of the kinetic theory of gases to describe collisions between gas particles, focusing on identical particles. Until now, in the kinetic theory of gases, we have only considered elastic collisions of gas particles with the walls of their container. However, in reality, gas particles also collide with each other. In the kinetic theory of gases, we assume that gas particles are very small compared to the distances between them. Nevertheless, their motion through space inevitably leads to collisions. The kinetic theory of gases provides a way to calculate the average frequency of these collisions. This allows us to describe many chemical phenomena, including the rates of chemical reactions. Let us start by clearly defining what we mean by a collision between gas particles. The kinetic theory of gases treats gas particles as point masses that do not interact via intermolecular forces except during collisions. Looking beyond the kinetic theory of gases, we recognize that at low pressures, intermolecular forces are generally negligible outside of collisions. At higher pressures, when particles are closer together, intermolecular interactions become more substantial overall. Nevertheless, even at low pressures, the forces acting during a collision between gas particles must be considered. Intermolecular forces become relevant when two particles approach each other closely and collide. A detailed treatment of collisions that fully include these intermolecular forces is well beyond the scope of this course. Instead, to describe collisions, we adopt a simplified model in which gas molecules are treated as small, hard spheres with a certain radius. These spheres are impenetrable, meaning that they cannot occupy the same space. The motion of two such spheres relative to each other is unconstrained, with one exception. If their trajectories would lead to an overlap, the spheres do not overlap, but instead collide and deflect. Thus, collisions occur when two spheres representing gas molecules attempt to occupy the same region of space during their motion. An excellent everyday example of interacting hard spheres is billiard balls. They interact only when they come into contact. We define a collision as an event that occurs when the geometric centers of two particles come, or more precisely attempt to come, closer than a characteristic distance, called the collision diameter and denoted as d-col. If gas molecules are represented as impenetrable spheres with radii r1 and r2, the collision diameter is simply their sum. For identical particles where both radii are the same, the collision diameter simplifies to 2r. Collisions depend fundamentally on how fast particles approach each other and not just on their individual speeds relative to the container. The relative speed between two particles is defined as the magnitude of the difference between their velocity vectors. This expression describes how quickly two particles are moving towards or away from each other in space. It takes into account both their speeds and their directions. To evaluate the relative speed of two particles, we must take into account that both particles are moving. This leads naturally to the classic two-body problem of mechanics. Rather than analyzing the full trajectories of both particles, it is more convenient to describe their behavior in terms of relative motion and the motion of the center of mass. For our purpose of studying collisions between gas particles, we focus only on the relative motion. The two-body problem is simplified by introducing the reduced mass, denoted by the small Greek letter mu, and equal to m1 times m2 divided by m1 plus m2. Here, m1 and m2 are the masses of the colliding particles. The reduced mass allows us to treat the two particles moving relative to each other as if they were a single particle of mass mu moving with the relative velocity v rel. In physical chemistry, it is often more convenient to work with molar quantities rather than those related to individual particles. For this reason, I introduce the reduced molar mass, denoted μm. Here, capital M1 and M2 are molar masses of the colliding particles. Now, an important point. For a system of gas particles in thermal equilibrium, the distribution of relative speeds between two particles follows the Maxwell-Boltzmann distribution, just like the distribution of individual particle speeds. The only difference is that the mass of a single particle is replaced by the reduced mass of the two particles involved. It follows directly from this principle that the mean relative speed between two particles, which we will use to quantify collisions, is given by the square root of 8 kb times t divided by pi times mu. This result assumes elastic collisions, which is fully consistent with the assumptions of kinetic theory of gases. For collisions between identical particles, these expressions simplify significantly. The reduced mass becomes exactly 1/2 of the mass of one particle. Substituting this into the corresponding formula, we find that the mean relative speed between two identical particles is equal to the mean speed of a single particle multiplied by the square root of 2. To visualize how collisions occur, we start by considering a model with only one moving particle. This moving particle travels through space, while all other particles are considered stationary. As it moves, it may collide with any stationary particle if its center comes closer than the collision diameter to the center of a stationary particle. This simplified model helps us to understand and quantify the frequency of molecular collisions. We now introduce the collision cylinder, a cylindrical volume associated with potential collisions between the moving particle and the stationary particles. It is defined as follows. If the center of a stationary particle lies inside this cylinder, then the moving particle is on a collision course with it. By this, I mean that a collision will occur provided the moving particle continues traveling in the same direction. In reality, a particle changes its direction after the first collision. Nevertheless, to define the cylinder, we assume straight line motion. The axis of the collision cylinder passes through the center of the moving particle and points in the direction of its velocity. Further, we will define the base of the collision cylinder, which is perpendicular to its axis and intersects it at the center of the moving particle. The moving particle is on a collision course with a stationary particle if, assuming it continues along its current direction, their centers come within the collision diameter at the moment they pass each other. This condition is satisfied whenever the distance between the center of the stationary particle and the axis of motion is less than or equal to the collision diameter. Alternatively, we can say that the projection of the stationary particle's center onto the plane of the cylinder's base taken along the direction of motion must lie within a distance equal to the collision diameter from the center of the moving particle. Both descriptions lead to the same result. The base of the collision cylinder is a disk with a radius equal to the collision diameter. The area of this disk defines the effective target area for collisions, which is known as the collision cross-section, denoted by small Greek letter sigma. The collision cylinder extends as far as the moving particle can travel in a short time interval, denoted as delta t. Importantly, we consider only one moving particle in this model, rather than many particles moving simultaneously. Therefore, we must use the mean relative speed as the relevant speed. Thus, the length of the collision cylinder is the mean relative speed multiplied by delta t. This gives the volume of the collision cylinder as the collision cross-section sigma times the mean relative speed times delta t. For the remainder of this module, we will focus on collisions between identical particles. Each particle has a mass m and a collision radius r, and the gas is characterized by a particle density n tilde. In the case of an ideal gas, the particle density is given by P over Kb times T. The collision cross-section simplifies to 4 pi r squared. And the mean relative speed is the mean speed of a single particle multiplied by the square root of 2. The number of potential collision partners within the collision cylinder is equal to the product of the particle density and the cylinder's volume. For identical particles, this expression simplifies to n tilde times sigma times the square root of 2 times the mean speed of a single particle times delta t. Now let us ask, how long does it take on average for the moving particle to collide with one of the stationary particles? To answer this question and determine the average time between collisions, t-call, we simply set the number of collision partners in the collision cylinder equal to 1. Solving for t-call, we find that it is equal to 1 over the square root of 2 times n tilde times sigma times v mean. We can expand this expression for an ideal gas, substituting the formulas for particle density and the mean speed of a single particle. And we can also express the latter result using molar quantities. The reciprocal of the average time between collisions gives us the collision frequency, denoted by Z. This is the number of collisions experienced by a single particle per unit time. For an ideal gas, this quantity can be expressed as shown here. Now we can use the average time between collisions to derive the mean free path, denoted by small Greek letter lambda. It is defined as the average distance a gas particle travels between successive collisions. To obtain the mean free path, we multiply t-call by the mean particle speed, obtaining 1 over the square root of 2 times n tilde times sigma. Note carefully, here we use the mean speed of the particles, not the mean relative speed. That's because the relative motion between particles has already been taken into account in the derivation of the average time between collisions. Interestingly, the formula for the mean free path shows that it is a purely geometric quantity. If we represent it as shown here, we can interpret the term V over n as the volume of a collision cylinder containing exactly one stationary collision partner. Since the collision cross-section sigma is the base area of the collision cylinder, the term V over n times 1 over sigma is the length of this collision cylinder containing one stationary collision partner. So far, this is pure and simple geometry. On average, the moving particle would have to travel this distance to go from one stationary collision partner to another one. However, in reality, the collision partners are not stationary, but are also moving. The relative motion of gas particles produces a factor of 1 over the square root of 2. That reduces the average distance traveled by an average particle between collisions in comparison to a model with stationary collision partners. In a gas sample at constant volume, when the particle density remains constant, the mean free path depends neither on temperature nor on the particle's speed. We employed the mean speed to derive the average time between collisions. However, when we determine the average distance traveled between collisions, the speed cancels out. As a result, the mean free path depends only on how many molecules occupy a given space and how large they are. As the particle density increases or as the collision cross-section becomes larger, the mean free path becomes shorter. This dependence is intuitive if there are more particles or if each particle has a larger size, collisions become more frequent, and the average distance traveled between them becomes smaller. For an ideal gas, we can substitute the particle density using the ideal gas law, obtaining this expression. Finally, we define the collision density, denoted here by ZAA, as the total number of collisions occurring per unit volume and per unit time. Here, with the subscript AA, I explicitly indicate that this quantity refers to collisions between identical particles. To calculate it, we multiply the number of particles per unit volume, the particle density, by how often each particle collides, that is, the collision frequency. However, there is one important correction, the factor of 1/2. If we were to simply multiply n tilde by z, we would count every collision twice. The usual explanation given to this situation is that for a collision between particles 1 and 2, we would count one collision of moving particle 1 with stationary particle 2 and another collision of moving particle 2 with stationary particle 1. To avoid this double counting, the factor of 1/2 is introduced. It ensures that each collision is counted only once. Substituting the previously obtained formula for the collision frequency, we obtain this expression. This expression indicates that the collision density increases proportionally to the square of the particle density, proportionally to the collision cross-section, which itself is proportional to the square of the particle radius, proportionally to the mean speed, which is proportional to the square root of temperature. For an ideal gas, the formula for the collision density can be expanded as shown here. And it can be also expressed in terms of molar quantities.